Cassio, Daniele, and Matteo, who were my students. And the idea was Karim Benakli is a phenomenologist, and he said there was a problem. He gave a seminar saying there was a problem with constructing Lagrangians for massive spin 3-half particles in electromagnetic background. So, I mean, it's a theoretical problem, but it's also a problem if you want to actually describe real massive spin 3-halves. So there are no fundamental massive spin 3-halves that we know of, but there certainly are bound states, which are massive spin 3-halves. String field theory, of course, I mean, string theory has massive spin 3-half particles in it, at least superstring field theory. So, so I said, well, I will not use superstring field theory. And my surprise was that nobody had even used RNS superstring field theory to describe in electromagnetic background. So, so people had done bosonic string field theory. So this was done a long time ago by Algebras and Nappi. And they showed how to construct Lagrangian for spin 1 and also for massive spin 2. So spin 1, of course, if it has no charge and you put in an electromagnetic background, you just get Born-Infeld. If it's charged, it's more complicated. And the spin 2 is interesting. I mean, so you get charged spin 2 moving in an electromagnetic background. And this was a new result that people outside of, well, massive spin 2 is not so trivial to describe either. So massive spin 2 is more is known about massive spin 2 than massive spin 3-halves. But even massive spin 2 has problems. And if you do it in 26 dimensions, so of course in 26 dimensions, there are no extra scalars in the game if you use string theory. And then you just get massive spin 2. But of course, what people are interested in is 4-dimensional massive spin 2. And then you get some extra scalars if you get it from string theory. But I mean, so it's massive spin 2 plus a scalar. And that you can describe using string field theory, and you get consistent propagation, etc. So massive spin 3-halves, we decided you could, of course, use the RNS formalism to do, well, spin 1 and spin 2, but nobody seemed to have done it. I think nobody did it. And we decided to use the hybrid formalism just because, well, the hybrid formalism in 4 dimensions has manifest space-time supersymmetry, as I'll talk about. So you get the massive spin 2 and massive spin 3-halves at the same time in a supermultiplet. And it's complicated, but it's not, I mean, you can write down easily what the equations of motion are. We didn't end up writing down the full Lagrangian, but we wrote down the equations of motion. And again, you get massive spin 3-halves and massive spin 2 and some extra scalars and spin 1/2. And if you wanted to do in 10 dimensions, then of course you would just get just massive spin 3-halves and massive spin 2. So the way we did it, we had manifest n equals 1, d equals 4 space-time supersymmetry. So as I'll tell you later, there's a very nice formulation of superstring field theory with manifest n equals 1, d equals 4. So if you want to have d equals 10 and manifest space-time supersymmetry, then the only way I know how to do it is using pure spinor formalism, and there we can write down equations of motion, but we can't write down actions, which is of course not surprising just because there's no manifestly space-time supersymmetric actions you can write down in 10 dimensions. Okay, so that's more or less a summary of the first paper. Of course, the methods we use are similar to the methods that Algebras and Nappi used for bosonic string theory. You just see how the electromagnetic background modifies the boundary equations, the boundary conditions. So it's an open string. So massive spin 2 is, of course, for open string theory, not for closed string. So you do open string in an electromagnetic background, and the electromagnetic background modifies the boundary conditions for the x's, and in the hybrid formalism also for the thetas. And then you just see how that modifies the Lagrangian and the equations of motion. Okay, so that's the first paper. Are there any questions about that before I summarize the second one? So of course, interrupt me whenever you want. You don't have to wait for me to stop. But okay, so the second paper was also used as hybrid formalism in 4 dimensions, but it was a little bit different. So of course, self-dual. So in 4 dimensions, self-dual Yang-Mills is, of course, used to construct instanton solutions of Yang-Mills. And in, of course, defining a self-dual field strength is trivial if you have a field theory action. But in string field theory, as you know, everything which is gauge invariant essentially vanishes on shell. So, so if you try to write a field strength, the thing you can write down is Q of V. Q of V is, of course, 0, at least to linearized order. So defining a stringy generalization of a self-dual field strength is complicated. Well, at least I don't know how to do it. But what you can do is use the fact that the self-dual field strength, half of the spacetime supersymmetry. So you can ask, what are the solutions of open superstring field theory which preserve half of the spacetime supersymmetries? At least, okay, so if you did it in 10 dimensions, that turns out that would force the solution to be on shell. We did it in 4 dimensions with just n equals 1, d equals 4. So asking that the solution preserves half of the spacetime supersymmetries, which are 2, that doesn't put it on shell, but at least that can be used to generalize the self. So we did that, and of course, what you find is that you have to work with the gauge field, not with the field strength. And you say, okay, the gauge field, of course, you want the gauge field to be preserved by half of the supersymmetries up to a gauge transformation. So if you work in the hybrid formalism, the spacetime act linearly. So you would never get corrections if you just asked that it was half spacetime, if it was preserved by half the spacetime supersymmetries, because they act linearly. But of course, the gauge transformations act linearly in string field theory. So if you ask that it's spacetime supersymmetric up to a gauge transformation, then you get nonlinear corrections, and that leads, if you do string field theory, those corrections start to give massive. So of course, self-dual Yang-Mills already has nonlinear corrections if you're doing non-abelian. But doing string field theory, then you also get contributions from the massive states. So we contributed the first massive contribution to instanton solution, to the self-dual instanton solution in the limit of large instanton size. Okay, so that, I mean, again, it's a problem that maybe is not what you do with this massive correction. It's not clear, but maybe if you could find out some more non-perturbative way of defining the instanton, that might be interesting. Just because you're trying to describe non-perturbative string theory, and of course we want to use string field theory, and at least for super Yang-Mills, instanton solutions play a large role. So maybe, of course, we know they're connected to D-branes in string theory, but how you construct them from superstring field theory is, well, at least for me, it's not clear. So that was the second paper where we did some computations. Essentially, Ulysses, who is here, did most of the computations to show that to show how to construct the massive contribution. I could say Cassiano, who's also here, he did most of the computations for the, well, together with Mateos for the first paper. Okay, so those are some applications. If I have time in the end, I'm happy to talk more about them. But I think the main thing I want to talk about is this super Poincare variant version of superstring field theory. So it's really D equals 4 super Poincare variant. So that's not in the title, but we still don't have a 10-dimensional super Poincare variant superstring field theory. But for some situations, 4 dimensions may even be more convenient than 10-dimensional. So the examples I gave earlier, 4-dimensional super Poincare variance is actually very convenient. And the fact that you can keep all n equals 1, at least for, so this is just open superstring field theory. Closed is not yet done. And at least for open superstrings, you know, it obviously contains D equals 4 super Yang-Mills, and it contains all the massive stuff. So there's lots of interesting things you can do. And in this case, you don't have to do any of those tricks that are necessary in 10 dimensions. So for example, there's no picture changing operators. There's no, what else? No spin fields, at least using this super Poincare variant version. And for me, it's very elegant. And in fact, this paper has lots of citations. So it has over, I think it has 280 citations I checked today. But all of the or 90, I would say 99% of the citations, they don't discuss the super Poincare invariant part. They just discuss the fact that you have Q and eta, and this was the paper that introduced the Westermino-Witten-like action. But that was like the first chapter of the paper. The other 3 chapters, which I found more exciting, was showing that you can describe the action in a super Poincare invariant way. So of course, the WZW-like action, when the paper was written, was just for the Nevers-Schwarz sector. Now, of course, that has been extended to the Ramon sector, but nobody seems to have picked up on the super Poincare invariant except for me and my students. So that's the main reason why I'm giving this journal club, is I think to try to get people interested in this paper, at least in the last sections of the paper. Okay, any questions up to now? Okay, so let me start with the basic introduction of open superstring field theory using this formalism. So you have Q and eta, and I think everybody probably knows what eta is. So eta comes from bosonizing the beta gamma fields. And normally, when in superstring field theory, you say, okay, so in Nevers-Schwarz string field theory, you say the fields are annihilated by V and have ghost number 1 and annihilated by Q. So that's what's called working in the small Hilbert space. So and when I write eta, I always mean eta 0. So I won't put the 0. It always means the integral of eta. And Q is, of course, the RNS. Here is TR. So these are the usual conditions for physical states. And of course, you can get them from an action. If V has ghost number is picture -1, you can get it from the action of VQV, where V is required to be annihilated by eta. But here, the idea is to work in the large Hilbert space. So what I'm going to define is a field phi, where the equation of motion is, so this has ghost number 0. And the equation of motion is Q eta phi equals 0. So this, if you work in terms of V, then of course V has the gauge transformations, delta V equals Q lambda, where you also require that lambda is annihilated by 8. So that's the usual description in the small Hilbert space. In the large Hilbert space, we're going to have a field phi with ghost number 0. And now the gauge transformation can be delta phi equals Q lambda, and I'll call it plus eta lambda bar. So because eta carries picture, lambda bar will also carry picture. So if phi has picture 0, let's suppose it has picture equals 0, then of course lambda would have picture 0, but lambda bar, because eta carries picture, you can see from here, eta carries picture -1 from this. So that means lambda bar should carry picture +1. Now the two, of course, are related. You're not going to get this independent description. The relation is you can always define V to be equal to eta phi. Okay, so that obviously satisfies eta V equals 0. And now you define this lambda to be just equal to eta. So let me call this lambda prime. Define lambda prime to be equal to eta of lambda. Okay, so that's the relation between the small and the large Hilbert space, and we'll always use the large one. So the large one, of course, has more gauge symmetries, okay, which will turn out to be convenient, especially when we want to describe the space-time supersymmetric version. Okay, now the action in terms of phi is very simple. So if phi has picture 0, then you can write the action as just phi. I feel like I write it like this: Q phi eta phi, which is of course equal to, I don't know if it's plus or minus, but phi Q eta phi up to total derivative. Now, the last ingredient I want to say, which maybe is a little bit unfamiliar, is ghost number. So Q, of course, has ghost number 1, but I'm also going to find eta to have ghost number 1. So that might be a little bit surprising. Normally, at least Frieden, Martin, and Schenker define e to the phi to have ghost number 1 and eta to have ghost number 0. It's more convenient to describe the ghost number such that eta carries ghost number 1 and psi carries ghost number -1. And then the ghost number, so called JG, is equal to psi eta plus BC. So you can see that this action here has ghost number 2. It doesn't have ghost number 3, it has ghost number 2. Okay, any questions up to now? So this is, of course, to linearized level. And now the question is how to generalize this to the nonlinear level. Okay? And the idea is you instead of having these as your gauge transformations, you generalize them to the nonlinear level by thinking of phi as being well, let me not try to write it explicitly. By thinking of these as being a Westermino-Witten model where Q acts, well, lambda act is the gauge transformation acting on the left of G. So just to remind you of Westermino-Witten. So Westermino-Witten, you have a matrix G, which is takes values on the world sheet. And the gauge transformations are of this type. G goes to lambda G plus G lambda bar, where lambda is holomorphic and lambda bar is anti-holomorphic. And then the action is of the form D squared Z and then there's another term you have to write, which is something like dt D squared Z. So the action is of this form, where G hat is a function of t, which has the property that when t equals 0, it's equal to 1, and it's equal to G when t equals 1. Okay, so this is the Westermino-Witten model, which I assume.
Sorry, Nathan, I have a question. It's just notational probably, but so this gauge variation you write, is it the gauge variation or this is the new G?
Yeah, I was thinking about this when I wrote it down. You're probably right. It's delta.
Because if lambda is 0, then this is 0. No?
Is this.
Okay. Thanks a lot. Okay.
Any other questions? Thanks. Okay, so in this framework, what one does is one thinks of D as being replaced by Q, D bar is being replaced by eta, and G is going to be e to the phi. They're like capital phi. So, of course, now it's a little bit more complicated because Q and eta are fermionic instead of bosonic. So that just means this becomes an anti-commutator instead of a commutator. But essentially, all the gauge transformations work in the same way. And of course, to linearized level, you'll find that delta phi is equal to Q lambda. So I probably shouldn't have called this lambda bar. Let me call it omega and omega. So what you find is that to linearized level, the transformation of phi is just what I want. Where the idea, this lambda, this object here, is the analog of something which is holomorphic because it's annihilated by Q. And this object here is the analog of anti-holomorphic, but it's annihilated by eta. So this part of the paper is well known. Maybe even everybody here knows it. But then the rest of the paper, nobody seems to, well, at least nobody has written papers about. So the rest of the paper is, okay, this is, of course, valid for the Navier-Schwarz sector of the superstring, but string field theory is more than just the Navier-Schwarz sector of the D equals 10 superstring. So for example, Bosonic string theory, you can write, it's any C equals 26, conformal field theory. So you could say, okay, this is any C equals 15, N equals 1 superconformal field theory in the Navier-Schwarz sector. But it turns out that this is much more general, and where this came from is starting with N equals 2, a worldsheet action with or a superconformal field theory with N equals 2. Now, a critical N equals 2 superconformal field theory has central charge C equals 6. And the classic example, or the simplest example, is where you have X and X bar, where each of these take, let me put it up and down, take two values. So A equals 1 to 2. And you think of this as being some complex two-dimensional space. So, so this is normally thought of as D equals 2, 2. And this was used, well, there's a huge paper with many, many authors discussing this first, and then Vafa and Oguri showed that this describes, for the open string, describes self-dual super-Yang-Mills. Now, it turns out self-dual super-Yang-Mills, if you try to write the action, there's an action you can write which is almost identical to this action. Where phi, it turns out, self-dual super-Yang-Mills has one physical degree of freedom. Of course, super-Yang-Mills, sorry, forget about the super. Self-dual Yang-Mills has one physical degree of freedom. Of course, Yang-Mills in 4 dimensions has 2, but if it's self-dual, it only has 1. And this phi is essentially that degree of freedom. And if you work out the action, you find that this action here describes 4-dimensional Yang-Mills. If you, so of course, instead of writing like this, it's D4x e to the minus phi. Now these, instead of D, you use dA, phi, dA plus dot dot. So this is the action for self-dual Yang-Mills. It's called Donaldson Action. And you can see that there's a direct relation between this and this, right? Between these two actions. So if you just think of phi, sorry, I'm not saying it right. If you think of your Q as being psi ADA and eta as being psi ADA. Then it turns out this action here reproduces this action here. Okay, so if you just plug in the N equals 2 superconformal field theory using Q and eta, and compute the string field theory action using Q and eta of this form. So these are just the N equals 2 superconformal generators. I'll talk more about that in a second. And I said something wrong, sorry. I apologize. This should have been epsilon AB psi A. We'll see why in a second. So I'll explain where this comes from in a second, but I just want to point out that the way this action was found was by knowing this action. Okay, so of course, I don't want to think of the d equals 2 is some application of, this thing was found with Never-Schwartz string field theory. It was actually the opposite. So that means that this n equals 2 superconformal field theory, thinking about it, is actually more basic. And I think string field theory, the goal is to find the most basic object, and then, of course, look for generalizations. And I think this is the most basic description. Okay, so in any case, let me say how this is related now. So the general case. So the idea is that an n equals 2 superconformal field theory has G plus and G minus and J, right? And of course, T. So this usually has conformal weight 2. This has conformal weight, these have conformal weight 3/2. This has conformal weight 1, right? And in this special case, these are very simple. This is just dx plus psi d psi. This is dxa psi a. This is dxa psi a. And this is just equal to psi a psi a. It's the same a that I discussed here. I guess I'm calling this bar. So. And I should call, let me just put a bar on here too. So this is equal to psi a psi bar a plus okay, this is easy to see as c equals 6. Okay, any questions up to now? Okay, now it turns out if you have c equals 6, there's actually a small n equals 4 algebra you can define. So it turns out this is J is of course a U1 J, but you can also define J plus plus, which I'll define to be epsilon AB psi A psi B. And J minus minus I'll define to be epsilon AB psi bar A psi bar B. So it turns out J plus plus and J minus minus commute to form an SU2. And if you commute that SU2 with G plus and G minus, you find you also get some new generators. So J plus plus with G minus, that's equal to G tilde plus, which in this case is equal to, sorry, this should be an up index, is equal to D bar X. This is equal to dxa psi b epsilon ab. And you can also construct with J minus minus, you can construct something called G tilde minus, which is just equal to dx bar a psi bar b. Okay, so these generators, of course, also carry conformal weight 3/2. And J plus plus and J minus minus, they all carry conformal weight 1. Okay, any questions? Okay, but now what you can do is you can twist. So any n equals 2 theory you can twist by just redefining T prime to be equal to T plus 1/2 Tj. And then what you find is that the operators G plus, G tilde plus, and J, they all have conformal weight 1. Whereas the operators G minus, G tilde minus, J minus minus, T carry conformal weight 2, and J plus plus carries conformal weight 6. So this can be done for any C equals 6, N equals 2 superconformal field theory. And now you can see that Q is just equal to G plus. If I think of this as dx. Let me write it again, sorry. So in the special case where we're looking at the D equals 2 theory, you find that G plus is equal to dxa phi a. G tilde plus is equal to dxa psi b epsilon ab. So this is what I said was supposed to play the role of Q, and this is what I said was supposed to play the role of eta. And if you use these operators in the superstring field theory I wrote down before, just plug in Q for G plus native, you get, as I said, the Donaldson action for self-dual. Now, this indicates that you can actually describe not just G plus and G tilde plus in terms of RNS variables. You can also describe G minus. So G minus turns out to be equal to B, the B ghost, and G tilde minus is more complicated, but it's something like B times the RNS picture changing operator. J plus plus in this case is equal to C eta, and G minus minus is equal to B C. And here you find that J is precisely what I told you before it was. So it's the ghost number. So you can think of the RNS string, at least the Nivers-Schwarz sector of the RNS string, as being an n equals 2 superconformal field theory with C equals 6. So these generators, of course, form a C equals 6 n equals 2 superconformal field theory, or even a C equals 6 n equals 4, small n equals 4 if you include these other generators. So this is what was called the n equals 2 embedding of an n equals 1 string, or the RNS string. So the natural way for me to understand this superstring field theory action is you write the action for any critical n equals 2 string. And in the special case where the n equals 2 string comes from this n equals 1 embedding, then it gives you the RNS string field theory action. But it's more general. It describes more than just RNS. It describes any n equals 2 critical superconformal field theory. So of course, this d equals 2, 2 theory, you're not going to describe as an n equals 1 string. It's not the usual 10-dimensional string. It's another theory, which is n equals 2 superconformal field theory. So this string field theory action is more general than just the RNS. And that's my point. So there's a way to describe this string field theory action where it describes the Nivers-Schwarz sector of the superstring, but also the Ramon sector. And the way to do that is not using the RNS formalism, but using this hybrid formalism. So that's what I'll describe next. So any questions up to now?
Just about the physical interpretation of the G tilde minus. Because if you go a bit further down,
yes.
See, all the operators, they have a nice interpretation, but this G tilde minus, it's B of Q and Xi.
Well, there's another way to write it, which might be nice. It's not nicer, but it's so it's clear it's Q with B Xi, right? Just to understand where this comes from, because B Xi is J minus minus. So I'm just using the definition of G tilde minus by the commutator of J minus minus with G plus. Okay. So that's, I know it has this form. But why this is, I mean, I don't know, does J minus minus have a physical meaning to you?
No, not really.
Okay, but that's just because of your biases, because you're forcing me to say, I want to think about the Nivers-Schwarz string.
I'm not forcing you. I'm just trying to get some intuition.
No, okay, so from, okay, so how can I say it? The eta ghost also is not the physical, I mean, maybe the zero mode has some meaning because you're used to the large Hilbert space. But for me, okay, the B ghost you can say has something to do with worldsheet reparameterization or something like that. But the eta ghost, I mean, that's just some, if Friedan, Martin, and Schenker didn't write their paper, you wouldn't even know what I meant by the eta ghost. So, so in any case, there are certainly ingredients here. Well, let me answer your question in a different way. The bosonic string is well understood. The RNS string is not. Okay? Picture changing for me is not some geometrical operation. Picture changing for me is some construction that people invented in order to construct fermions in the INS string. So for me, I mean, for me, the INS string is an incomplete story. And I mean, I've had this discussion before, but I get annoyed when people think that the INS is the end of the story, because it just has too many missing features. But anyways, that's another. Okay, so any other questions? Okay, so the next thing I want to do is to show how to make space-time supersymmetry manifest. So is it correct that I have until that I have 50 more minutes? Is that right? Somebody told me at the beginning it was an hour and a half. Is that correct?
Yeah, that's correct.
Okay, so I have time. I just have to know how I want to pace myself. Okay, so if you want to describe, so as I already said at the beginning, if you want space-time supersymmetry manifest and you want to write down an action, there's not much you can do, because space-time supersymmetry, even for the field theory, we only know how to make space-time supersymmetry manifest essentially for 4-dimensional actions. So we can do some things in 6 dimensions using harmonic superspace. But for anybody who's worked with harmonic superspace, it gets very messy very fast. So you can write simple actions with space-time supersymmetry in 5 and 6 dimensions. But I think if you want to write the most general action with 4-dimensional, with space-time supersymmetry manifest, 4 dimensions is probably, I think, the best you can do. Now, the philosophical point, which is maybe this has some importance. I mean, of course, we live in 4 dimensions, which is another reason why 4 dimensions is interesting to describe. But there might be some reason that, okay, I don't know, this is conjecture. But so I only know how to make space-time supersymmetry manifest in 4 dimensions. Okay, so at least to write down actions. So which means to go off shell. Okay, so the way we're going to do it is we're going to introduce variables similar to Wesson Bagger. So we have xm, theta alpha, and theta bar alpha dot, where m is now 0 to 3, and alpha dot to 1 and 2. And then, of course, the superstring is 10-dimensional, so we're not going to try to describe the superstring in 4 dimensions, but we're going to treat the 6-dimensional Calabi-Yau variables separately. So we're going to use the variables y for the Calabi-Yau variables, and we're going to have a fermionic counterpart, which I'll call gamma and gamma bar, so I equals 1 to 3. And you should think of these as being the in the RNS. So I'm only going to describe open strings. Okay, so as I mentioned, closed superstring field theory is not yet developed using this formula. So I'm just describing the open superstring. And so this bar has nothing to do with anti-holomorphic on the worldsheet. The bar is the same kind of bar as we introduced here for the G equals 2, 2 theory. So these 6 fermions are going to play the role. It turns out they're related to the, if you're doing in RNS, of course, you'd also have 6 fermions. Okay? But of course, in RNS, the other degrees of freedom would be very different. You'd have the X's, but you'd also have BCs and beta gammas, and also, of course, the 4 psis. So this would be an RNS. But we can count degrees of freedom. So we see we have 4 fermions here, thetas and theta bars. We, of course, have 4 X's. Okay, that doesn't change. But we have all these extra stuff. So here we have 6 fermions and 2 extra bosons. So we want to have the same number of degrees of freedom. So I'm going to fermionize these. So let me write beta as being dc e to the minus phi, and gamma is a to e to the phi. So now we have 1 extra boson, and we have 8 fermions, right? Because they're the BC, Psi eta, and 4 psis. So what we're going to do is we're going to introduce conjugate momentum to the p's and p bars, which I'll call p alpha and p bar alpha dot. And we have introduced 1 extra boson, which I'll call rho. So these are fermions. And this is a boson. So this rho boson is going to play the role of this phi. And the thetas and p's are essentially going to play the role of the psi's and the BC ghosts and the psi and 8. And then you might think, well, why? That doesn't make sense. How can ghost fields play a role in matter fields? So I think of these as all matter fields, because thetas are like the superpartners of X. So if X is a matter field, theta should be a matter. But remember, when you try to write down Ramon vertex operators using RNS, the spin fields, of course, are built out of the psi's, but you also have these terms like e to the minus phi over 2. So what we're going to do is we're going to think of P as being something like e to the minus phi over 2 times the spin field sigma alpha. So it's built out of matter fields and ghost fields. So in this description, which is called the hybrid formalism, the thetas and p's are built out of the ghost and matter fields in RNS. Okay, so there's no one-to-one map between matter and matter. So I don't think it's worth telling what the precise relation is between these variables, but it turns out there's a field redefinition, which takes you precisely from these variables to these, which preserves all the OPEs. So I can tell you something else, which is gamma I is equal to the gamma ghost times psi I. Gamma bar I is 1 over gamma times psi bar I, where 1 over gamma is defined to be c e to the minus phi psi bar. So it turns out I didn't tell you what the conformal weight of these fields are. The conformal weight of psi and psi bar, of course, plus 1/2. The conformal weight of gamma I is going to be 0 because of this gamma ghost. And the conformal weight of gamma bar is going to be 1. Similarly, the conformal weight of theta is going to be 0, and the conformal weight of p is going to be plus 1. So all the fields in this theory have integer spin conformal weight, which is important because if we want space-time supersymmetry to be manifest, you should not have to sum over spin structures. So in this description, there's only even spin structures. There's no, since there's no, there's no spin structures. Forget even. I mean, there's not. All the fields are periodic on the worldsheet. That's what I'm trying to say. So it's like Green-Schwarz-like. Okay, so of course it's not Green-Schwarz because we're in 4 dimensions and we have these extra stuff, but it certainly is similar to Green-Schwarz. And you can show that in light concave, this reduces to light cone Green-Schwarz. Okay, any questions?
Sorry, Nathan, can you hear me?
Yes.
Yeah, so these variables yi and yi, they are defined in terms of psi or something like that?
No, the y's are essentially the same as in the RNS.
So
Dimensional Calabi-Yau variables.
okay, sorry, I see. Good, thanks.
Okay, any other questions? Okay, so I told you there's a field redefinition. I don't think it's worth telling you precisely what the field redefinition. I hinted at certain pieces of it. But when you do the field redefinition, you find that G plus and G minus have a simple form. So G plus is equal to D alpha e to the rho, plus something I'll call G6 plus. I'll tell you what that is in a second. No, I can tell you what it is already. Plus dy bar I, gamma I. And G minus is equal to d bar alpha dot the minus rho, plus dyi. So you see this part coming from the Calabi-Yau is precisely the n equals 2 superconformal generators that you would use to describe the C hat equals 3 superconformal field theory for the Calabi-Yau. But unlike in RNS, I mean, this was the BRST operator. Remember, G plus was supposed to be the BRST operator in RNS. Because the BRST operator doesn't decouple into a 4 and 6 dimensional piece. But after doing this field redefinition, you find that G plus does decouple. And G minus also decouples. So the 4-dimensional part of the superconformal field theory is just C hat, or if you like, C equals -3. And from the Calabi-Yau, you get C equals 9. Okay, so it's 2 decoupled N equals 2 superconformal field theories. Similarly, you can also work out what J is. So J is equal to D rho plus gamma I, gamma bar R. And of course, T is equal to just the sum of the stress tensors from the 4-dimensional part and the 6-dimensional part. Now, something I didn't tell you yet is what D alpha is. So D alpha is a supersymmetric combination of the P's and the thetas. So it's equal to, using Wesson-Bagger notation, something like this. Okay, there's also a term with 2 thetas and a theta bar, which I'm not going to write down. But something like this. So it turns out that D alpha, if you think of P alpha as being like d theta, and dx as being like d dx, then you see that this is similar to D alpha of space-time supersymmetry, Wesson-Bagger, right? So small d alpha is the worldsheet version of the supersymmetric, the fermionic capital D alpha. So these objects are manifestly space-time supersymmetric, right? Because just like capital D alpha commutes with the space-time supersymmetry generators, G plus is clearly space-time supersymmetric. The reason why you need to multiply by these gammas and 1 over gammas is so that the capital gammas are also space-time supersymmetric. So in RNS, of course, psi's are not space-time supersymmetric because the spin field contains dependence on psi. But after multiplying by these gammas, you find that the capital gammas, sorry, there are too many gammas. After multiplying by the small gammas, the capital gammas commute with the, or anti-commute with the space-time supersymmetries that preserve the Calabi-Yau. So this is manifestly N equals 1, D equals 4 supersymmetry. Okay, any questions? Okay, so now, of course, what we're going to
I have
do,
one question. Is there any physical interpretation for the, sorry, is there any physical interpretation for the remaining supercharges compared to the N equals 1, D equals 10?
remaining. I didn't tell you what they are, but I mean, that's what the remaining means G tilde plus and G tilde minus. Is that what you mean, remaining?
No, these are the worksheet, but in terms of space-time, if I'm thinking of RNS in
What do you mean
D equals
remaining
10,
one? Which remaining one?
usually for the open string, we have N equals 1, D equals 10 supersymmetry.
I don't know, but I'm compactifying Calabi-Yau. These are the only symmetries.
Okay, so this like this other
If I work on a
supercharges.
torus, no, if I work
Okay.
on a torus, then there are other generators. Is that what you mean?
Yeah.
So if I compactify in a torus, yeah, and they're messy. Of course, they're still preserved, but they're messy. You can write them in terms of the thetas, but they're going to be a
Okay.
mess. So there'll be things like, I don't know, things like gammas. They'll have gammas. They'll have e to the rows. They'll have p's in them. There'll be linear combinations of these things. Okay. Any other questions? Okay, so I didn't tell you what G tilde plus is, but since we have J, actually, I never told you how to get J plus plus. So J plus plus you can get by computing the exponential of the integral of J. And J minus minus, so this turns out to be equal to e to the row times e to the minus row, sorry, times gamma cubed. Gamma cubed is, you know what I mean, right? gamma I, gamma j, gamma k, epsilon I, j, k. Maybe I'll just write and j minus minus is equal to e to the plus rho times gamma bar, gamma bar. And from that, you can construct g tilde plus. So g tilde plus is easy. It's d bar alpha dot, d bar alpha dot. Now you have e to the minus 2 rho times gamma, gamma, gamma. And g tilde minus, you want, is equal to d alpha, e to the 2 rho times gamma bar again. Now the action is, of course, only going to involve g plus. And I forgot to write the other term. Sorry, there's another term here, which is plus e to the minus rho dyi gamma j, gamma k, epsilon I, j, k. And here you also get another term. So the other term, I'm just going to multiply this thing times this. So I'll get e to the rho, e bar yi, gamma bar j. Okay, so sorry, this should be close. Okay, so these are the operators which are going to enter into the superstring field theory action. Okay, so you have G plus and G tilde plus. And it's the same action as before. Just everywhere you see Q, you substitute this, and everywhere you see 8, you substitute this. It turns out that that describes a certain sector of the superstring. Because I didn't tell you yet what is phi. Okay. So I told you in the when I was doing the Navier-Schwarz sector, I said phi should have picture 0. So here's Navier-Schwarz. This phi here has picture 0. But we know that, of course, we want to describe also the Ramon sector. So it'd be silly to do all this and then just describe the bosons. So we have to do more. So we're going to allow the states to have non-zero picture. And now I have to tell you how the picture enters into the equation. So it will turn out that in the Navier-Schwarz, if you describe just the 4-dimensional sector of the superstring, that's the sector of the superstring which has no dependence on the Calabi-Yau. It turns out you can uniquely define picture in terms of R parity, or R weight, I guess, not R parity. Where if you remember Wessenberger, theta alpha has R weight plus a half, and theta bar alpha dot has R weight minus a half, which means, of course, P alpha should have minus a half, and P bar alpha dot should have plus a half. So you assign the picture to be equal to the R weight. What that does is it makes, for example, the photino, of course, there's a chiral part and an antichiral part of the photino. The chiral photino would be in the picture, the vertex operator for the chiral photino would be in the plus a half picture, or gluino, and the antichiral gluino would be in the minus half picture, the vertex operator. And if you only discuss the 4-dimensional Calabi-Yau independent, that's completely consistent. And for that sector, it turns out the string field theory action I wrote down before is finished, it's complete. But actually in this paper, I do more. I discuss the whole superstring field theory action, including the Calabi-Yau dependent sector. And then it turns out our symmetry is not the conserved symmetry, because our symmetry doesn't commute with the SO6 of the internal degrees of freedom. So that means you have to introduce more string fields. And that turns out to be, in fact, what I think is the most interesting part of the paper, but probably which almost nobody knows anything about. So it's how to include all the string fields, all the spectrum in terms of this language. So, of course, Navier-Schwarz and Ramon, okay? Okay, before I do that, are there any questions? Okay, so just to, if you restrict to compactification independent states. And you just replace phi. Now, of course, phi is a string field. So it can depend on all these variables, x, theta, p, etc. But not on the Calabi-Yau stuff. Then it turns the action is the same. Action. Okay, but now we want to include the compactification dependent state. So now we have to be more clever. Okay, so what we're going to do is we're going to first allow all pictures. So the problem is, of course, picture changing. So in RNS, you know that if you start allowing non-zero pictures, then you have picture changing operators, and the number of picture changing operators you need to include depend on how many vertex operators you have in the Ramon sector, how many in the Nevers-Schwartz sector, etc. Whereas this action I wrote down has no picture changing operator, so there's nothing you can do. You're stuck, right? So we're going to start with a description of the string which has all pictures. And in order to use this description, of course, we have to have more gauge symmetries. So the way we're going to do this, so this has nothing to do with the hybrid formalism. This is something unrelated. So suppose you have a vertex operator which will allow all pictures. So of course you can write it as v to the n, where vn has picture p. I'm sorry, has picture n. Okay, so far I haven't done anything. Now suppose we want to discuss the physical states. So what we're going to say is we're going to say q plus eta on v equals 0. And we're going to allow gauge transformation delta v is equal to q plus eta of lambda, where lambda can also carry any picture you like. It turns out this describes, at least to linearized order, describes the physical spectrum. The way to prove that, at least if v has a finite number of pictures, so v has finite number of terms, it's on shell. The way to prove this is essentially use the fact that eta has trivial cohomology. And Q also, if you work in the large Hilbert space, Q also has trivial cohomology. To show that Q has trivial cohomology, all you need to do is construct an object such that anti-commutator with Q is equal to 1. And that's easy to do. So this is equal to 1. So if you work in a large Hilbert space, both Q and eta have trivial cohomology, and you can use that to show that, that this spectrum, you can always reduce V to be in a single picture. And once you reduce V to be in a single picture, then of course Q plus eta V equals 0 implies that Q of V equals 0 and eta of V equals 0, because they carry different pictures. Okay, so this is a description, at least at linearized level, of a theory in the large Hilbert space, or in the Hilbert space with no restriction of picture. Okay, any questions about? There were some papers later written about this by Kreuter, where he called this democratic string field theory or something like that, because it allows all pictures. Okay, now it's clear. What we want to do here is have G plus, this is obviously going to be replaced by G plus G tilde plus on V equals 0. And delta V equals G plus G tilde plus of lambda. So that's the more general description. Okay? So I haven't told you anything about writing down an action. This is just linearized equations of motion. Okay, any questions? And when I write this G plus and G tilde plus, I always mean the 0 mode. Okay. So G plus, you should think of as Q, and G tilde plus as the analog of eta. Okay, now in the description we had before, G plus has two terms, right? It has the term G squared e to the rho, and it has the term, here I wrote it, dy bar gamma. So I'm going to call this G4 plus and G6 plus. And similarly, G tilde plus has two terms. G tilde plus was d bar squared, e to the minus 2 rho gamma, gamma, gamma. I'm going to call this G4 tilde plus. Then the other term was e to the minus rho gamma, gamma dy. IJK. So these are the fields, these are the construction I used before, and I'm going to call this G6. So you can see that they all carry different rho charge. This carries rho charge +1, rho charge 0, rho charge -2, rho charge -1. That's going to turn out to be relative. And now instead of expanding V in picture, I'm going to expand rho, oh, sorry, 5. Instead of expanding V in picture or phi in picture, I'm going to expand phi in rho charge. I do that in order not to break supersymmetry, because spacetime supersymmetry carries picture, but it doesn't carry rho charge. So each of these phi's will be spacetime supersymmetric. Phi n is e to the n rho times something. Okay. But I'm not going to put any restriction on the picture. Okay, so phi n can depend in arbitrary ways on the thetas and p's and anything it wants. Okay. Any questions? Okay, now I can do the same trick as we did before. Sorry, I wasn't supposed to have. So I'm going to do the same trick as we did before. And show that most of these phi's can be gauged away. Now it turns out that G plus and G tilde plus, they don't just have two terms, they have 4 terms. Because you have 4 different rho charges. But G4 plus, it's easy to show that G4 plus and G tilde 4 plus are trivial. That's just because you can invert them in the same way as before. So G4 plus with theta squared e to the minus rho equals 1. And similarly, G tilde 4 plus you can invert. In this case, it's theta bar squared e to the 2 rho gamma bar. That means that you can simplify the description, but now instead of having 1 field as we had before, which was just a single picture, you need 3. So it turns out you can gauge away everything but phi minus 1, phi 0, and phi 1. So you use the gauge degrees of freedom. So of course, you have this gauge invariance here. You can show that you can gauge away all of the fields except for these 3. Phi 0 is essentially the thing we had before. We were strict to the Calabi-Yau independent sector. If you want to include the sectors which depend on the compactification, you need to include also phi 1 and phi minus 1. Okay, so now one just has to look at the equations of motion. So of course, to linearize the order, it's easy to figure out what the equations of motion are. Because here's G plus G tilde plus phi, and you just plug in these fields and see what you get. So you can see, for example, the equations of motion are of this type. You get 3 equations of motion. I wrote them down here. My notes, 1 second. Here they are. Okay, so you get G4 plus. There's not many things you can write down just because of the rho charge conservation. So you get something like this. G4 plus. Sorry. G tilde 4 plus. Sorry, getting mixed up by my notes. G6 plus phi minus 1. So this equation comes from this equation here. If you just act with G4 plus, that essentially kills the last term. Similarly, you get the complex conjugate of this. And finally, you get the equation G4 plus So you see the three string fields, they talk to each other. Okay? So this is, of course, to linearized level, but now you want to generalize to nonlinear level. Okay, so so that's the thing that I'm going to tell you how to do, which is how to write an action, or first of all, how to generalize this to the nonlinear level, and then how to write an action which reproduces those equations of motion. And that is the open superstring field theory action with manifest n equals 1, d equals 4 spacetime supersymmetry. And of course, you can do it in a flat background or in a Clapeyau background. And okay, the applications I already mentioned, at least two applications. Of course, there are hundreds of other applications if people want to think about it. Okay, so how to get the nonlinear version of this? Okay, so the intuition for getting the nonlinear version of this is going to come not by thinking about Western-Witten, but by thinking about n equals 1, d equals 4, by thinking about d equals 10 super Yang-Mills written in terms of n equals 1, d equals 4 superfields. So of course, d equals 10 super Yang-Mills has 16 supersymmetries, and only 4 of them will be manifest. But of course, we can certainly write down super Yang-Mills, 10-dimensional super Yang-Mills in terms of the 4-dimensional superspace and see what you get. And this was in fact done by, trying to remember all the authors. So Siegel, Sagnotti, Marcus and Sagnotti. I don't remember when was the paper, but a long time ago. And essentially you use the same way that the Western-Witten-like string field theory was guessed by starting with the action for self-dual Yang-Mills. It's essentially straightforward to guess the action for this full 10-dimensional superstring field theory with all this superspace, starting from the super Yang-Mills action. So essentially, you just have to generalize their derivatives into these G4 plus, G6 plus, etc. Okay, so what are the variables that appear in 4 dimensions? So if you work in d equals 4 super Yang-Mills. So the super Yang-Mills fields, when you decompose d equals 10 in terms of 4-dimensional superfield, you get the usual, I don't know what it's called, vector multiplet that describes n equals 1, d equals 4 super Yang-Mills. But then there's 6 other components of the gluons, right? So 10 dimensions, the gluon has 8 components. So 2 of them sit in V, but the other ones are contained in, sorry, I should use 5. I'll call it omega. The other components are chiral and anti-chiral superfields, which carry an index. So let me call it So these are chiral superfield and antichiral superfield. So if the states don't depend on the 6 dimensions, then these would of course be the scalars. So these describe the 6 scalars. But of course, if you're working in flat space, then instead of being scalars, they would be just 6 components of the 10-dimensional gluon. So these are the fields that appear in, you can think of it as either n equals 4, d equals 4 super Yang Mills written in terms of n equals 1, d equals 4 superspace, or you can think of it as 10-dimensional super Yang Mills written in terms of n equals 1, d equals 4. Any questions? And then you have these covariant derivatives. So you have things like del alpha equals e to the minus v d alpha e to the v. Del bar alpha dot is equal to d bar alpha dot. And then you also have covariant derivatives from the 6-dimensional translations, which take the form of del bar I. Del I. So you see that omega and omega bar play the role of the connections, as they should, because it's coming from the six components of the gluon. Whereas the four-dimensional components of the gluon are in V. So they appear, I mean, if you expand out these supersymmetric derivatives, if you know Westenberger, this gives you the usual connections for 4 dimensions. So you see that these covariant derivatives, of course, automatically include the nonlinear corrections, and the equations of motion are easy to write down. The equation of motion you can write in superspace is just coming from requiring that certain components of the connections vanish. So this is reminiscent of string field theory, that the field strengths, the vanishing of the field strengths are essentially the equations of motion, right? Okay, so this is super Yang-Mills. And now you just have to figure out, well, how is this related to what we were doing before? Okay, so it's clear that del alpha is going to be related to G plus. Remember, del alpha is related to G4 plus, which was d squared e to the rho. Del bar alpha dot is related to G bar 4, G tilde 4 plus, which was, if you remember, was something like d bar squared e to the minus rho gamma gamma gamma. And these covariant derivatives are going to be similar to, so del I is going to be related to G6 plus. Del I is like G tilde 6 plus, which remember was something like T Y. I'm worried about the anyways. And finally, del bar I is going to be G6. Probably switched the up and down index when I did this. But in any case, the point is, if you remember, there was something similar that we did for the n equals 2, 2, or the d equals 2, 2. We had this relation of the n equals 2 superconformal generators and the derivative. So it's the same kind of relation here. And so now what we see is that an easy way to generalize this linearized equation of motion is to start with the equation of motion G plus G tilde plus equals 0. So this was the linearized equation of phi equals 0. And now we're going to generalize this to the equation of motion. I'll write it like this: G plus G tilde plus the equations of motion are going to come from requiring that the interacting version of the G4 plus and G6 plus and G tilde 4 plus and G tilde 6 plus, that the square of this is equal to 0. So that's the analog of these fields, requiring that these field strengths vanish. So it will turn out that now I just have to tell you what G tilde 4 plus and G tilde 6 plus. So G tilde 4 plus, G4 plus is equal to e to the minus phi 0 G4 plus e to the phi 0. G6 plus is equal to e to the minus phi 0. Let me call it omega bar. Tilde 4 plus and finally G tilde 6 plus is equal to G. So the point is that you should, sorry, the slides are far away, but the idea is that these four operators get translated into these four operators, where omega is equal to, right, G tilde 4 plus phi 1, and omega bar is equal to G4 plus phi 1. So this is supposed to be thought of as chiral because it's annihilated by G tilde 4 plus, and this is anti-chiral. So the claim is that the complete equations of motion are described by this equation here. So I didn't tell you what the action was yet. I just told you what the equations of motion are. But it's completely straightforward to show that these equations of motion, if you expand, for example, in the massless contribution, so phi 0, of course, starts out as the Super-Yang-Mills field, V, and then there's massive contributions. Phi minus 1 starts out as omega I e to the minus rho. And phi plus, that's not quite right. This is actually what I should have written is this. Let me get a different letter. I'll explain this. Where the field I called omega before is equal to d squared. And omega bar is equal to. Remember, I told you that omega was chiral and omega bar is antichiral. So that's the relation between these. Okay, so my point is that if you expand these three string fields in terms of their massless contribution plus the massive contribution, obviously, the massless contribution reproduces using these equations, reproduces precisely what you want. Okay? Precisely these equations here. This is straightforward. Okay, so the last thing to do is just write down the action which reproduces these nonlinear equations of motion. And that, again, if you had to do it just without knowing anything, you'd get lost. But But this action was already constructed, the action for the 10-dimensional super Yang-Mills in terms of 4-dimensional superfield. So we can use their construction and use this dictionary for going from the super Yang-Mills operators to the string field theory operators to easily write down the action. Okay, now I'm just going to write down, I mean, I'll tell you what it is. I'm not going to write down all the terms. So you have a WZW model for the 4-dimensional sector, which are essentially what I told you before. You just replace Q with G4 plus and eta with G tilde 4 plus. And it's the same action before. But now you have another term, which is WZW, where now Q is equal to G6 plus and eta is equal to G tilde 6 plus. So you have both of those terms, for example, because the equation of motion you want for phi 0, it involves both the 4-dimensional and 6-dimensional. So you need both of those terms. Then you get a coupling. So that's described just in terms of the 4-dimensional V or phi 0. That only depends on phi 0 because WZW only depends on phi 0. But then you get other terms which couple them to the Calabi-Yau. So I'll write down what those are. And they look something like Chern-Simons terms. It should not be surprising because the field theory action for the Calabi-Yau degrees of freedom is a Chern-Simons action. Then you get the complex conjugate. Okay, then finally you get a contribution which couples phi 0 to the Calabi-Yau degrees of freedom. So that's right down what it is. It's complicated, but just to be complete. Okay, so this is the complete action. So it's the sum of Wess-Zumino-Witten terms, two Chern-Simons-like terms, and then finally you get an interaction term which couples the Calabi-Yau degrees of freedom with the 4-dimensional degrees of freedom. Okay, so that's essentially all I had to say. So of course, I think there are many things that can be done with this. If you want to describe compactifications, but also if you just want to describe the general structure of open string field theory. And of course, lots of generalizations one can try, for example, closed string field theory. I don't know, I guess, well, you guys have more ideas than I do about what can be done. Okay, so I'll stop there for a question.
Okay, thank you, Nathan, for the nice presentation. Are there questions from the audience?
Hi, Nathan.
Hi.
So is it important that the 6-dimensional part is a Calabi-Yau for this formulation, or could it be something else?
It's important that it preserves n equals 1 d equals 4 supersymmetry. So it can preserve more. It could be torus, and then you have more symmetries. But you need to preserve at least n equals 1 d equals 4. Otherwise, this construction doesn't work. So one way to say it is the theory is supposed to be an n equals 2 superconformal field theory with c equals 6.
I see.
We know that if you preserve n equals 1 d equals if you have an n equals 2 superconformal field theory, you know you can construct have n equals 1 d equals 4 spacetime supersymmetry. So the two are related.
I see. All right. Yeah. Thanks.
So I don't see any raised hands. Are there any
I
other
have one more
questions?
question, if I may.
Oh,
I didn't want to take too much
No, please feel free
priority
to.
here. But it's not quite related, but you mentioned, that the WCW action, you guessed actually also in analogy with the self-dual action of Young-Mills.
Yeah.
So this I didn't know, that that was somehow the origin of it. Is that easy to understand?
Okay, I don't know what you mean easy, but
Or to motivate, so to say.
I think it's obvious. Once you realize that the action written down is for an n equals 2 superconformal field here, not for an n equals 1. So as I said, it has no role, and 8 has no meaning as an n equals 1 in an n equals 1 superconformal field. It has no meaning.
Yeah.
You really need this n equals 2 structure to give it a meaning, and where it's g tilde plus. So, and then the obvious question is, well, the simplest representation of an n equals 2 is this self-dual Yang-Mills. So, so the problem with the bosonic string is that the ground state is not Yang-Mills. The ground state is tachyon.
Mm-hmm.
You would never guess phi cubed phi plus phi cubed by thinking about Yang-Mills or tachyons. But in this case, the ground state is just, in fact, the only state is self-dual Yang-Mills. So it's clear that, that the actions have to be related. So.
I see. Yeah. All right. Yeah. Let's see. Thanks.
Can I ask a question?
Yeah.
Can you perhaps explain a little bit why the closed string field theory side of the story is so difficult in this formalism?
Sorry, why it's what?
The closed string. So you said that with this formalism, it is not known how to build the closed string field theory. Like I don't know. So you could also compactify type 2B on a Calabi-Yau, right? And
so certainly. So sorry. So the worldsheet theory is fine. You can compute scattering amplitudes.
Right. Yeah.
But as you know, the WZW for closed strings gets much more complicated.
Okay. So
But from the worldsheet point of view, there's no problem at all. So of course, this hybrid formalism, there's no problem with doing it for closed string.
So there is, for example, there is a formulation for the heterotic string in Wezumino-Witten form for heterotic string field theory. And
yeah, I agree. I don't think it. As I said, the only people who have worked on this are me and my students. As far as I know, at least I've written papers. I mean, my students.
Okay.
Okay, no more questions? Ivo?
No, I'm good. Thank you.
Good.
Great. Thanks.
Okay, so let's thank Nathan again. This was the last seminar of the year, and we will resume in January. But we're still preparing the list of upcoming speakers.
So I'm not sure. Am I supposed to go to this Zulip thing or not? I don't know what that is. So.
No, it's up to you.
Okay. But should I? I mean, that's the question.
Okay, I think it's nice because there are some people there already interacting. For example, I see often Ashok Sen and Ted,
Okay,
for
so
example.
I should just stop that. Okay, I understand. So I should just stop by occasionally and